In this lesson, we are going to talk about the determinants. We are going to define what is the determinant of a square matrix, and we are going to see how this type of determinants are calculated. So, you need to remember that a square matrix is a matrix that has exactly the same number of rows as columns, and how operations are carried out with real numbers to make the calculations. So we will start by saying that the determinant of a square matrix is a number that we associate with the matrix, and that it will help us to know in a faster way, for example, if the matrix has an inverse or not. If the matrix has a row or column, that is a linear combination of the others. And it will also help us to calculate inverse matrices by the method of the adjoints. During the lesson, we will denote the determinant for any square matrix in this way, which you have on the screen in red, so that it is easier to describe. We will start by defining the determinants of order 2. The simplest determinant would be the order 1, matrix 1 times 1, but a matrix 1 times 1 is a number, with which the number itself is the determinant. So the next order of matrices would be the 2 times 2, 2 rows, 2 columns, and its determinant is defined as the number that is multiplied by the elements of the diagonal main. A, 1, 1 times A, 2, 2, and subtract the product of the elements of the secondary diagonal A, 1, 2 times A, 2, 1. That gives us a number, which is what we call determinant. For example, for the matrix 1, 7, minus 2, 4, if I multiply 1 times 4 and I subtract the product of 7 times minus 2, I get that the result is 18, as you can see, a number. Well, if we generalize this to determinants of order 3, then the definition, matrices of 3 rows with 3 columns, the definition is similar. Of course, here we have more elements, with which more factors appear to add and subtract. We would do the product of the main diagonal, A sub 1, 1 times A sub 2, 2 times A sub 3, 3. The product of the parallel, A sub 2, 1 times A sub 2, 2 times A sub 1, 3. And the product of the other parallel times A sub 3, 1. That is with positive sign, and then we subtract the ones of the secondary diagonal. A sub 3, 1 times, A sub 2, 2 times, A sub 1, 3. That would be the first term that we subtract, the parallel times the second term, and the other parallel times the one on front, the third term. As you can see, there are sums and subtractions of products of 3 elements, each one of a row and a column. Well, for an example, we could make this determinant, for example, of the matrix 1, 7, 3, minus 2, 4, 0, 0, minus 1, 3. We multiply diagonal by the main one, the parallel, the other parallel, which is a positive sign. And now we subtract the product of 3 times 4 times 0, the secondary diagonal, minus 1 times 0 times 1, and minus 2 times 7 times 3. The result is 60, as you can see, a number as well. Well, this definition is a little difficult to remember. A good way to remember it is with the one that is known as Sarus's rule, which allows us to know that the main diagonal plus the other parallel times the one in front, and the other parallel times the one in front. All these go with a positive sign. And with a negative sign would go the secondary diagonal, its parallel times the one in front, and the other parallel times the other front. This is a rule that allows us to remember that the sign carries each one of these products in a more visual way. Well, before generalizing what would be the determinants of order 2 and 3 to order n, let's see what properties they meet, since the properties will help us in the calculation of the determinants. So, we will start by saying that the determinant of a matrix is the same as of its transpose matrix, which simplifies the calculation. I put the examples with a size of 2 times 2, although it is fulfilled for 2 times 2, or 3 times 3, and we will see that it is fulfilled for any order, but with 2 times 2 it is easier to see. So, if all the elements of a line are null, the determinant is also, which we would not have to calculate, we would directly put that it is worth 0. If a determinant is changed between itself, 2 parallel lines, rows, or columns, the determinant maintains the absolute value, but changes the sign. Let's see here. 1, 7 minus 2, 4 is worth 18. If I change the first and the second, minus 2, 4, 1, 7 rows, then it is worth minus 18. The next property is that if 2 parallel lines of a determinant are equal, 1, 1, 7, 7 are equal, then the determinant is null directly. The next property tells us that if all the elements of a line are multiplied by the same number, that is, as if it could take out a common factor, then the determinant is multiplied by that number. For example, 321 minus 2, 4, as you can see here, there is a 3 that I can take out a common factor. This is 3 times 1 and 3 times 7. Then I can take out this 3 and multiply it to a determinant with smaller numbers, which is easier to calculate. Well, notice that this is an important property of the determinants, and above all, that it is differentiated with the product of a number by a matrix. In the product of a number by a matrix, the number multiplied all the elements of the matrix, while in the product of a number by a determinant, that number is only multiplying a row or a column. That is an important difference. Well, if we continue with the properties, the next one tells us that two parallel lines of the matrix are proportional, then that implies that the determinant is null. 2. 14 is proportional to 1, 7. Therefore, the determinant is directly null. The next property is that if a row or column can be decomposed as a sum of two components, then we can decompose the determinant also as a sum of two determinants. And the next property that is also very useful in the determinant calculation is that if a line is added to a multiple of any other parallel, then the determinant would not vary. For example, the 1, 7 minus 2, 4. If I add the second column to the first column multiplied by 3, as you can see, 1 plus 7 times 3, and minus 2 plus 4 times 3, that gives me 22, 10, 7, 4. Then the two determinants are worth the same. This determinant is worth 18, and this other determinant is also worth 18. This property is very important because it will help us to simplify the calculation of the determinants, especially of superior order. Well, if we continue with the properties, the next property, before we can explain it, we must know a series of definitions. For example, given a square matrix, A, of order n times n, we call a complementary submatrix of the element A sub ij. That is, the element of the row I and column j as the matrix that results from suppressing the I row and the j column in the matrix. For example, if I have this matrix and I want to calculate the submatrix complementary of this 3, for example here, which is the element of the row 1 column 2, then I simply have to eliminate the row 1 and the column 2, and what is left? 0, 3 minus 1. 3 is a matrix of a lower order, obviously, which is called a complementary matrix of this element 3, of the element of the row 1 column 2. Well, since it is a square matrix, we can also calculate its determinant. If we calculate the determinant, it is called minor complementary of the element A sub ij. That is, it is the determinant of the complementary submatrix. In this case, for example, the determinant of this submatrix is 3, because that would be the minor complementary of this 3 here. And if we add a sign to that 3, which will depend on the element A sub ij of the position in which it is located, then it is called the adjoint of the element A sub ij. That is, it is the determinant of the complementary submatrix, with a sign that depends on the I and the j of the row and the column in which it is located, because it is minus 1 raised to I plus j. If I plus j is even, it will be positive. And if I plus j is uneven, it will be negative, depending on the sign, obviously, of the determinant. For example, for this 3, the determinant was 3. But since it is in row 1, column 2, it changes the sign, and it changes to minus 3. That would be the addition of the element 3 that we have here, of the element of the row 1, column 2. Well, this allows us to say that the determinant of a matrix is equal to the sum of the products of the elements of a row or column line times its respective adjoints. What does this mean? Well, if I have this matrix and I want to calculate its determinant, it is enough to choose a row that I want and develop by adjoints. The determinant will be A 2, 1 times its adjoint, A 2, 2 times its adjoint, and A 2, 3 times its adjoint. Remember, if this matrix is 3 times 3, each of the joints is of size 2 times 2. We are reducing the calculation of a determinant 3 times 3 to the calculation of 3 determinants 2 times 2. We could also have chosen a column, and it would be exactly the same. It can be a row or column, whatever we want. For example, for this matrix, 1, 3 minus 2, 0, 7, 3 minus 1 minus 2, 3. If I choose that column, for example, and develop by adjoints, well, I already have to calculate 1, 2, and 3 determinants 2 times 2, which are, in theory, easier. And also, since this is multiplied by 0, because one of the elements is 0, this I would not even have to calculate it. Then the more 0 there is, the better, since we have to calculate less. Well, the determinant value is 4. This property can be applied to any determinant of order 2, of order 3, as we will see, and of superior order, as we will see next. Because how do the determinants of order n define? Well, by generalizing the determinants of order 2 and order 3 as a sum of all the possible products of n elements, one of each row and each column, with their sign or with the sign changed according to a certain criteria that I do not tell you at this moment. Well, this is a generalization of what we have seen. Therefore, this definition allows that all the properties that we have seen for the determinants of order 2 and 3 are met. Therefore, from now on, to calculate determinants of superior order, we are going to apply those properties, especially the last one that we have seen, which is the one that helps us the most. In fact, if I want to calculate this determinant 4 times 4, then I choose a row, for example, 2, 0, 7, 3, because it has a 0, and thus I save a determinant and I develop by adjoints. 2 times it's a joint, 0 times it's a joint that I do not put it because 0 times something is 0. 7 times it's a joint and 3 times it's a joint. Notice that the sign depends on the position that the element occupies, because this here is the adjoint. Thus, I have reduced the determinant 4 times 4 to 3 determinants 3 times 3, which with the rules of Sarus we know how to calculate, and the determinant value is 450. As you can see, if I have zeros, it simplifies, because I have to calculate a determinant less, then the more zeros I have, the better. What we are going to do is apply the properties that we have seen of determinants that are fulfilled for any type of determinant, to calculate determinants by trying to do the greatest number of zeros possible. That is, we are going to do zeros in a line, row, or column. We choose by using those properties of the determinants. And then we will develop the determinant by the elements of that line by adjoints. What does that mean? For example, if I want to calculate this determinant that we have calculated before, we can develop it with row 2, 0, 7, 3. But it is also much more useful if I choose, for example, this column, so that you can see that things can also be done with columns. And I use the property that given any row or column, I can add or subtract a multiple of another parallel without changing the determinant value. Let's do that. If in row 1 I subtract 5 times the row 3, this becomes a 0. The other numbers also change, obviously, but that becomes a 0. So I already have a 0 here and a 0 here. And if in row 3 I subtract the row 4, then I have another 0 here. So I move on to this determinant, that if I now develop by adjoints for this column, as you can see, only an adjoint is saved. Only a determinant 3 times 3 is saved. And I avoid calculating the 3 that we have put before. The determinant value obviously is the same, 450. And we are going to apply this always for any type of determinant and for any order. For example, this matrix is 5 times 5, so we do the same. I choose a row or column, whatever I want, and I do operations of that style. Column 1 minus 2, column 3, column 4 minus 5, column 3, etc., etc., to get the largest number of zeros possible. That is, if it can be O minus 1. And now I develop by this number, by the adjoints of that row, so I only have to calculate a determinant 4 times 4. We do the same, more operations, we choose a column, we do operations so that we make zeros, and I start to have to calculate only a determinant 3 times 3. That determinant of 3 times 3, I calculate it with the Sarus rule, and it turns out that the determinant is worth minus 1197. As you can see, we can do both operations with columns and with rows. Be careful, because this can be done in determinants, operations with columns and rows. But this type of operations cannot be done with columns if we are working with Gauss method systems. In Gauss method, it only admits operations with rows, just like in the inverse calculation by Gauss method, which only admits operations with rows. In determinants, we can do both types of operations. Well, with this, we have seen what is the determinant of a square matrix, what properties it fulfills, and how they are used to calculate the determinants.